Hello, good morning or good afternoon, ladies and gentlemen. Greetings from sunny Czech Republic and the IDEA StatiCa headquarters, where we broadcast today's webinar focused on precast beams and its stability problems and how they can be solved in IDEA StatiCa software. So welcome everybody. Let me introduce who will guide you through the webinar. I will moderate it and help and assist our concrete expert, Orsholia Kartali. Orshi, how are you today?
Hi everyone, thanks, I'm well. I'm excited to share you the news regarding the new lateral torsional buckling analysis in Beam.
Pretty cool. We're all excited. So let me continue to explain you that we run this webinar on the GoToWebinar platform. Those who are not familiar with it, I would like to inform you that you are muted by default, and you can still insert your questions into the questions panel. So feel free during the webinar to do so, and we will answer your questions on the chat during the webinar. We will pick a question for the loud answer at the end of this webinar, and those answers that or questions that will not be covered during the webinar will be covered after the webinar via email. Okay, so feel free to ask questions for the topic or even off topic. And for today's agenda, what the webinar will be about. So as we said, as you saw in the invitation, it's the lateral torsional buckling of precast concrete beams. So Orshi will give you a theoretical introduction to the topic. Then she will demonstrate to you and explain how IDEA StatiCa solves this problem, what tools do we have in which app, and shows you a live demo of that in the third part, and at the end, Q&A and some more information from my side, and that's it. This will take probably something less than 1 hour. So enjoy this webinar. I'm giving word and the floor to Orshi now. And turning off our cams. So Orshi, the floor is yours. Have
Thank
fun.
you, Adam. Thank you for the introduction. And let's move to the theoretical part of our webinar, theoretical intro. So what lateral torsional buckling is? Lateral torsional buckling, or LTB in short, of precast beams is a stability failure mode that is caused by combined sideways bending and twisting. It occurs especially when the beam is slender and laterally unbraced. In this mode, the beam twists and displaces laterally. This effect leads to the sudden loss of load-bearing capacity, even if the material stresses are below the yield limit. Unlike gradual yielding, LTB, lateral torsional buckling, can happen without any visible warning beforehand. The word lateral means sideways or horizontal displacement of the compression flange, while torsional means twisting about the beam's longitudinal axis. The combination of these two effects makes LTB a coupled instability problem. Why lateral torsional buckling matters and why is it dangerous? It is a sudden failure mode. It occurs without any visible warning. A beam that can look fine in one moment can twist and collapse if stability is lost. This effect can occur at much lower loads than expected. The beams may fail well before reaching their bending capacity. It is critical during construction because temporary conditions are more critical than final in-service conditions. Why? Because precast beams are often unbraced during lifting, transport, and installation. It is a big safety risk. Lateral torsional buckling during construction can cause accidents, damage, and even fatalities. Therefore, proper design against lateral torsional buckling is a key safety responsibility of every engineer designing precast beams. And why are the long prestressed beams especially vulnerable? One thing is their slenderness. They have long spans and relatively narrow cross-sections usually. They have long unbraced lengths. During lifting, transport, and erection, the top flange of the beam may not be laterally supported. They used to have open cross-sections, which are much more prone to twist under bending. The loading during construction, such as self-weight, pre-stressing, and lifting, may cause LTB to happen before permanent supports are in place. So what are the critical stages that we are talking about? It is the lifting after casting. This happens in a precast factory when the beam is moved after it has been cast, is moved to the storage yard. Then the transport situation, the transport to construction site. On these pictures, you can see how are usually these long, slender precast beam transported to construction site. Because of their length and their dimensions, they are transported in a way that one end of the beam lies on a truck and the other end of the beam usually lies on a trailer. And as you can possibly imagine, lateral stability or any sort of stability issue can happen during this transport situation, so it is critical to assess proper restraint conditions and all. Then next critical stage is the lifting to the final position, which happens on the construction site when a beam is being moved to its final place. And the next stage is the final supports, because even if a beam is moved to its final position, we may not have any lateral bracing in place yet. So the beam is can be still prone to lateral torsional buckling. LTB itself is a big engineering challenge. It is a complex behavior which involves interaction between bending, torsion, and lateral displacement. Because the complexity, it is very sensitive to geometry and imperfections. The analytical solution is very complex, or can we say impossible, but when an engineer attempts to use this problem, solve this problem analytically, it usually takes many iterations. It is highly dependent on support and restraint conditions. And also, lateral torsional buckling is not always covered well in codes. They do provide some guidance, but usually do not cover unusual shapes or temporary states. So engineers must often go beyond code-based formulas and use advanced analysis tools. What are the available methods for the calculation? At the moment, there are three main calculation methods widely used by engineers. The first one to mention would be the basic equations from design codes, the basic formulas. These are for the simple cases and are very useful for the preliminary design phase, but they are usually limited to simple geometries and without taking imperfections or construction stages into account. Then you could use a linear buckling analysis, which gives critical buckling load factor, and it is useful for identifying LTB modes and buckling shapes, but this too is without imperfections or nonlinear effects. Then we have a third option, GMNIA, which stands for geometrically and materially nonlinear analysis with imperfections. This is the most accurate representation of lateral torsional buckling, assesses the real capacity, including nonlinear effects, and it allows us to model asymmetric cross-sections and real construction stages. So here we have our first poll, and I would ask Adam to administer the poll for us all.
Yes, of course. So I will launch the poll now for you. Do that right now. So now on your screens, you can, if you have the screen full width, full size, full screen of the GoToWebinar, you can click and you can select even multiple answers if you have such. So please vote your answers, how you deal with buckling currently in your projects. Or how about you? If you go back in years into your practice as a concrete structural designer, how did you deal with this problem?
Well, during my practices as a design engineer, I mainly design cast-in-place concrete structures, which are not prone to lateral torsional buckling. But when we were designing precast beams, we usually stuck to the code-based formulas, which many times meant that the beam did not fulfill the code-based formula conditions. Therefore, we had to go back to square one and increase the dimensions of the cross section or do bigger modifications like that. So we did not use any really advanced analysis, and I'm now really happy that these analyses are much more widely available.
Okay, so it used to be a struggle. Today, not anymore, as we will see in a moment. That's good. And I will close the poll now and show you results of our public voting. And as you can see, the answer pretty much resonates with your experience. So also our attendees today rely mostly on the code-based formulas, which of course have their limitations and often, as you said, lead to over-designing the precast beams. Good. So thank you very much, ladies and gentlemen, for this poll. And Orsi, you will continue and with the explanation and demonstration, right? How to do it a better way.
Of course. So I'm very happy to say that the GMNIA analysis is now available in IDEA StatiCa Beam. It has been available since version 24.1. With that, structural engineers now have a practical and accessible tool to tackle lateral torsional buckling in complex precast beams, which I think is a huge leap forward for the design safety and accuracy in precast design. So moving on to the more practical part of the webinar, I will show you how to define the necessary inputs correctly so you can easily use this design tool that was made for the engineers to be used in their everyday work. So you would follow a typical workflow of input and design in the application Beam, as I will show you in a minute. So input of geometry, cross-section, supports, loading, prestressing tendons, combinations. Definition is the same as it used to be always. All the construction stages can be defined as usual. And when you are done with this preliminary design phase and you move to the actual concrete design, choosing which checks you want to perform for ultimate limit state or SLS checks, now you have a new option in the lateral stability selection for this advanced calculation. So up until the version 24, we used to have the simplified check available, which is a code-based formula from Eurocode, or the option to not calculate lateral stability at all. And now we have a new option to choose the advanced calculation, which is the full GMNIA analysis. To start from the beginning, I would like to introduce you to the material models used for this calculation. We are in ultimate limit state at the moment. So here are the diagrams for concrete, reinforcement, and pre-stressing. For concrete, we use a parabolic rectangular diagram. For reinforcement and pre-stressing, we use bilinear diagram with horizontal or inclined top branches. Some info for the model preparation. So this GMNIA analysis for lateral stability is available only for newly created projects from the version 24.1. So after you watch this webinar and you, for example, become excited to start using this feature and you have some older projects on hand that you designed in version 23, 24, let's say, when you open those older projects, you do not have the ability to turn on the advanced calculation, but all new projects created since version 24.1 have the option for the advanced calculation inside. All precast beams are supported. They can be single span or continuous. So cast in situ concrete beams are not calculated for LTB, but prefabricated concrete beams can be calculated single span or continuous. One additional information: when you are in the first phase of your design and you are defining the project data, you have the option to choose a straight or polygonal beam loaded in 3D. And by choosing this option, you have the ability to input any loading on eccentricity or even perpendicular to the beam, not only vertical loading. And if you have such loading and you input it, this can have a critical effect on the lateral stability calculation. So use that if there are any loads on eccentricity. The practical demonstration will now start. We will use a simple example of a prestressed saddle beam. The reason I picked this saddle beam, it is a basic tutorial example. For example, if you go to our website and you want to try what I'm just doing here during this webinar, you can go to our support center on IDEAStatiCa.com, and in our tutorials, filtering out the concrete applications and the beam application, we have the structural design of a prestressed concrete saddle beam. Going through this basic tutorial, you will get the example that I'm showing you today, and we will demonstrate the use of this new workflow on this beam. So I will go to the application. This is the environment of IDEA StatiCa Beam, and I already have this model prepared. I will not start from scratch, to not use valuable time on preliminary design, but concentrate on this new workflow. So as you can see, we have a saddle beam with hinged cross sections. This is a slender eye cross section. The beam is simply supported. We have pre-created load cases based on the construction stages input into the projects. We have self-weight, already some pre-stressing defined. I will show you how the tendons look like going into this tendon module, so we get the whole picture what we are dealing with. So in this tendon module, I will take a look at the tendons layout. We have two pre-tension tendon groups. Take a look at the cross section at the middle of the beam. This is how the tendons are aligned within the cross section. So we see some equivalent load effect of the pre-stressing here. We also have some superimposed dead load and variable load introduced later in the construction stages. Our combinations are pre-created based on code requirements. So if I take a look at my combinations, we have a set of combinations for every construction stage based on Eurocode. The construction stages are, as are typical for such a beam: casting, transfer of prestressing, storage yard, transport, final supports. Then there is superimposed dead load introduced, and end of design working life at 50 years. So let's say I've completed the first phase of my design with inputting loading, pre-stressing, defining the construction stages correctly, and now I have calculated this project, moving on to the design phase. So in concrete design, I have the option to check which code checks I want to perform. For ULS and SLS, I have every check marked, of course. And for lateral stability, I will not calculate stability calculations at the moment and show you the results with just the essential code checks that are required by default. So checking the results, of course, I have some reinforcement introduced into the beam, as you can see on the cross sections. So showing the summary of results, you can see that I fulfilled every code check for ULS and SLS required by Eurocode. But what I didn't do the lateral stability calculation just yet. So now I am satisfied with this first stage of design. I can move on to the lateral stability calculation, going back to concrete design data, and turning on the lateral stability calculation, the advanced calculation this time. With this, when I go to the lateral stability step, I have all these options available. What I will do, I will go through these steps one by one, which is leading me through the design step by step and through the calculation. First is the data tab. Here I have the design member. Now I have just one design member because this is a single span, simply supported beam. If I would have continuous beam, which consists of 2, 3, or more beams, I would have the whole list of beams here, and I would assess every precast beam separately for lateral stability. Design situations. I have 5 design situations in total: lifting, transport, second lifting, final supports, and end of design working life. So for every design situation, we have a set of settings that we need to correctly define. We have the option to define concrete strength, user-specified concrete strength, and user-specified concrete modulus. If I do not input user-specified values, the values are taken automatically from the material properties of concrete. I wanted to add that for the design situations, you see the age is listed here. The ages for transport, final support, and end of design working life are taken automatically from the construction stages defined here. And the ages for the lifting and the lifting 2 are approximated from these ages of final support or transport respectively. Of course, you can manually edit the value. This is input in days, so you can input the correct age of concrete, which is very important because then the material characteristics go into the calculation based on the concrete age. So maybe the most important setting is the lateral imperfection setting. So initial geometric lateral imperfection can be set either geometric imperfection or overall imperfection. I will show you in the presentation some additional information through that so you can understand it better. So this applies for lifting, transport, and basically all design situations that we need to define some initial imperfection. If we define initial imperfection as geometric imperfection, then this value of geometric imperfection is taken into the calculation, and the rheology strain, the strain from shrinkage, is added as a load during the calculation. The geometric imperfection, if it is defined by the code, which is the default value, is the length of the beam divided by 300, or you can input user-defined value for geometric imperfection. The other option is to have overall imperfection, which is, for example, let's imagine you go to a construction site and you see a beam that is visibly curved like a banana, and you as the engineer are now wondering whether it is even safe to lift this beam, to transfer this beam, or it will break in half during lifting or lose its stability somehow. So if there is a visible, measurable imperfection, you can measure that value and input it directly into the application, and this value goes directly into the calculation without adjustment, without rheology strain added. So going back to the application, this is how we define the imperfections. I will go with the geometric imperfection. This value will be code defined, which is the L divided by 300, 16 meters divided by 300. And this is an initial value of imperfection for the calculation. Lifting method can be defined with inclined slings or vertical slings. I will use the inclined slings in this example, and there is the need to define the height of the crane hook, which is now 5 meters. It is measured from the top of the beam, and this value defines the angle of the inclined slings, which will have an effect on the horizontal load which goes into the beam from lifting. The lifting points on the left and the right side can be defined separately. They do not have to be symmetrical, so you can define a different position of lifting point at the beginning and at the end. You have to define the length of the lifting eye, which is measured from the top surface of the beam. It can even have lateral eccentricity if it is not placed exactly in the center, and the distance from the beginning and the end need to be correctly input. So this is all that I have to define for the lifting situation. Then moving on to transport. As you may remember from the presentation, such precast beams are transported in a way that one end of the beam lies on a truck and the other end lies on a trailer. So we have this as a displayed here. This support here represents the truck and the other supports represents the trailer. The truck is a perfect hinge that is free to roll, and the trailer is as a hinge with a defined rotational stiffness. Definition of concrete strength and imperfection stays the same as was described for the lifting, but the truck definition and trailer definition is something new here. So we can have the truck at the beginning or at the end of the beam. We have to define its position and the bearing height. The bearing height of the truck is measured from the bottom surface of the beam. So it is like a half meter from the bottom surface of my beam. The trailer is defined with its position 1.5 meters from the end and the number of axles. So I can have 1 until 5 axles. Now I have 3 axles defined in this trailer. The rotational stiffness of one axle has to be input. So going back to the presentation to show you some additional information to that. So bearing height is measured from the bottom surface. Rotational stiffness of one angle, the recommended value here lies somewhere between 340 and 680 kilonewton meter per radian per dual tire axle. And there's also a need to input initial lateral tilt, which is the tilt of the road. The default value is 1.5 degrees, but it can go up to 5 degrees in curves. So keep that in mind to define it properly. Okay, so transport situation is defined. Moving on to the second lifting. Here I basically have the same input options as for the first lifting, but of course I could have different settings. Instead of inclined slings, I could have vertical slings and so on, but the settings remain the same. Final support design situation. This is the situation when the beam is already in the final position. Again, I can define the material properties, imperfection, the same way as for the first situations. And what is new here is I have to define the end support. The support type can be either elastomeric bearing, which is typical for bridge structures, or we can have fork support type, typical for building structures, or a bearing pad with a dowel. These last two types, like fork and bearing pad with dowel, they can have a defined stiffness. They can be either perfectly stiff or with a user-defined stiffness. So I will use a fork support for this example. And let's take a look how this support type looks like. So elastomeric bearing, as I said, can be seen mostly in bridge structures. We could have a fork or a bearing pad with a dowel with defined stiffness. Okay, so whatever I define here in this situation for final supports, we have to remember that all these all these settings will be used in the end of design working life too. So we are already in the final support stage, and we are defining like definite restraints for our beam, and whatever is set here is automatically taken to the end of design working life. What is changing, however, is the age of concrete and the loading. During the final support design stage, I have the option to input intermediate supports. These can help with stability issues, and we can input 1, 2, or however how many we need in our beam. Intermediate supports can be placed to the top of the cross section, to the center, or to the bottom. We can define their number, and they can be stiff or user defined. And whatever I define at the final supports design situation is used for the end of design working life. As I said, the only difference is the age and the loading, because at the end of design working life, we have much older concrete, and also pre-stressing losses do occur. And also for the loading, we can have variable loads and superimposed dead load taken into account at end of design working life. So this is for the settings. Then moving on to the next step is the combination. So we are in a non-linear calculation here. We have to define separate combinations that will go into the non-linear calculation separately. The combinations need to be defined manually, or at least checked manually. As a default value, you can have some combination predefined here, but it's important to check whether you have the correct load factors for permanent loading and variable loading introduced. So for every design situation, we have to have the proper combinations input, including the loading factors. What is important to mention is the dynamic factor for permanent loads. This applies for the lifting and transport situations. We need to take into account some dynamic effect. The default value of this factor is 1.3, which is a rather safe value for the dynamic effect, but the dynamic factor can go up till even 2.5 in extreme situations on uneven terrain. So this has to be also checked or input manually. So I'm just going through the combinations whether I have everything defined. End of design working life. We have variable loading already, including superimposed dead load here with the corresponding load factors correctly input. Okay, so combinations should be fine. Now I can move on to the analysis results. In this step, I can launch the calculation, and now the geometrically and materially non-linear calculation is running. What we are doing in this calculation, imagine as we input the geometric imperfection in the first phase. So we literally curve the beam with the value of the geometric imperfection. This is an initial imperfection, and then we start the calculation, whether it is lifting the beam or transporting the beam. There is some increment of this initial imperfection given the calculation, and then we get the results. What I can see immediately is that I have some non-conformities here. The calculation stopped because of divergence of nonlinear calculations. What does this mean? This basically means that the beam lost its stability. Where are we? We are at the end of design working life situation, which was the last one. So what I need to do after the analysis is complete, I have to go through each and every situation one by one and check out how the results look like. So in lifting 1, I have all the results without warning. I am fine. There is no loss of stability. Then going to transport, I have the nonconformity again, which means that the beam lost its stability. I have to do something about that. Then second lifting, no warning, successful calculation. Final supports, again, everything looks fine. And end of design working life, we have some problems here. Stability was lost. Remember that final supports and end of design working life are basically the same in terms of restraints and boundary conditions. They just differ with the age and the loading. So it looks like the beam could not withstand the additional loading introduced after the final support stage, and we have to do something about that. So now what I do is I go back to the data and try to do something about transport and end of design working life. This transport, I will now try if some adjustments will help with my stability calculation. I will try to introduce 4 axles, place it a little bit closer to the middle of the beam to stabilize it more. And at the end of design working life, as we do not have any settings here, everything is set in the previous step, I will introduce some adjustments in the final support. So I will input some intermediate supports that will help me probably with the lateral torsional buckling effect. So I will have one intermediate support at the top of the beam in the middle, and let's try how this affects my results. In the meantime, I wanted to show you one interesting and very useful article which was written by my dear colleague Tomáš Svoboda, which is, I think, the most comprehensive article available in our support center for lateral stability calculation. It may be rather long, but it guides you through the whole process of the design. All the settings are thoroughly explained for this lateral stability calculation. So if you want to try it for yourself and you cannot find any information, everything is written here, including values, including recommended values from code, and so on. So let's see if we have results already. Yes, I will check out the situations of transport, no warning, and like no warning. So it means that the beam this time could withstand all the loading without loss of stability, and we can now explore the results after a successful calculation. The results come in the form of reactions, internal forces, and deformation. This beam in the design phase, as I input any loading, there were no transverse load effects, there were no perpendicular load effects. I loaded this beam just vertically, and the tendons were also symmetrically input. So what I had in my results were only bending moments around the y-axis, and now if I check out the bending moment around the y-axis, around the z-axis, I see that there are some bending moments forming. Let's check out, for example, the lifting situation. When we have lifted this beam for the first time, I have some transverse effects. Also, if I check out the torsional effects, there is something that comes from this lateral stability calculation. If I check out the deformations, this is maybe the easiest thing to understand what is happening here. So the deformations in the y-axis, deformations uy, if I show the initial deformations, this value is the one that was input as a geometric imperfection, which is the length of the beam divided by 300. It is the initial imperfection. Then we can display the increment of the imperfection from the nonlinear calculation and the total deformation. So we have our results, but what can we do with that? Obviously, we want to take these additional internal forces, these additional effects from lateral stability into our code checks, take it into account somehow. It can be done very easily. Going through these next steps, check settings, leave all the default code checks checked. Going to the check positions, I need to input some sections where my beam will be checked. I input 2 sections, one near the support and one at the middle. And with just one click on this detailed button, I push all these results, including the lateral stability calculation, into our application called RCS, which stands for Reinforced Concrete Section. And this application is for code checks. So what I see here are the results from the calculation. And these results are already with lateral stability effects taken into account. What you can see here are these little plus or minus marks at the sections. It means that the geometric imperfection was input on both sides of the cross section. If we have an asymmetric cross section, this is very important to try and input the imperfection on one side, then on the other side, because one effect can be bigger than the other. So these check values are already with lateral torsional buckling calculation. If I check, for example, the internal forces, you can see that I have some effects, some bending moments around the weak axis already. This used to be 0 before, some torsional effects, and also some additional shear force that was not there before. What it looks like, the beam can withstand all these effects, including the lateral stability calculation. So if I want to explore the results in detail, I can go through the overall check out the capacity for the combination of normal force and bending moment, the shear checks, the torsion checks, or the interaction. If my section, if my beam could not withstand the effects, the additional effects that were created by this additional calculation, I would see it immediately here in the result status, and I could adjust, for example, the reinforcement, going into the reinforcement editor and try whether it helps me or not. But now I can confidently say that this beam will not lose its stability, given the fact that I did a combined calculation, not only for the necessary ULS checks and SLS checks, but also including the advanced lateral stability calculation. So I will check out whether I have some more information that I maybe forgot to mention. Yes, so we have the known limitations of this calculation. At this moment, only ultimate limit state calculations are available, with SLS calculations being under development, and automatic calculation of creep has not been implemented yet. This too is being developed. And this method, this advanced calculation, is available only for new models created since the version 24.1. So this was everything from my side. And now I will ask Adam whether we have some questions that we could answer on the spot.
Yes, I'm back. We do have questions, and as I see in the questions panel from my side, all of them are already answered. So if you have some more, please input them. We have a few more minutes of this webinar. And I picked one to read loud and to conclude this part of the webinar from Paulo, asking about, I will just read it loud. How is the pre-stressing modeled? Is it as an external loading or using tendons as finite elements? Does it have stabilizing effects on the structure?
Well, this is an excellent question. Thank you. Yes, this is important to explain because to answer the question in short, pre-stressing in IDEA StatiCa Beam is modeled with tendons being finite elements that are connected to the finite elements of concrete on an eccentricity. If we wouldn't do that, and if we would model the pre-stressing using outside loading forces, imagine that the pre-stressing effects would push on a beam from both sides. We would introduce huge forces from the two sides pushing on our beam. And then when we would curve the beam with this imperfection, this geometric imperfection, it would immediately lose its stability because of this huge pre-stressing pushing on both ends of the beam. But this doesn't happen in reality. Pre-stressing tendons do, in fact, have a big stabilizing effect on structures. And as a pre-stressed beam is about to lose its stability, is about to come out of its shape, pre-stressing tendons have the tendency to pull it back into shape. So it does have a big stabilizing effect. And yes, we have it modeled as a finite element to have this effect corresponding with reality.
All right. Good, thank you, Archie. So I will now switch the presenter to myself and conclude this webinar. So let me do that. Just find the proper slide. There we go. So thank you very much, Orshi, for your demonstration, introduction, and comprehensive information. I have one message for you for today's webinar, and that's our special offer. We are going to slightly increase our prices for our products because we are widening our investments and development, and we are bringing new tools, new features into our software. So we need more resources, and our software is becoming much bigger with the latest version and the version to come. So that's the reason why. But still, there is chance if you got interested to buy for the old prices that are at the level of year 23. So if you are interested, just scan this QR code, or you will get an automatic email as a summary of this webinar in 3 days with the link to this offer as well. So that's an opportunity to upgrade or enlarge your license pool in your companies, something like that. And for this, I have a second poll. That's a very simple question. If you are interested by this special offer, if you are interested in having IDEA StatiCa in your software portfolio or in upgrade or any kind of that. So let me run this poll now so we can vote. So a simple yes or no. Of course, if you select no, nothing happens. If you select yes, it's probable that somebody from our network will contact you, or you can do it yourself. Get in touch with us. Right. I'll wait a couple of seconds so that we have everybody voted. Okay. So I will now close this poll. Thank you. And I will continue with the conclusion. So after the webinar, you will be asked with a short survey how you liked the webinar actually. And the recording, that's the essential information, the recording of today's webinar will be uploaded to the webpage and our YouTube channel today afternoon. So in a few hours. So you can replay that, you can share it with anybody. It's all accessible for free, of course. For those who are new to IDEA StatiCa world, you can get the free trial version at our webpage. Just navigate to ideastatica.com and click 14-day trial. You will get immediate access to the full functionality of the software. And last but not least, the support and learning part of our webpage. As Orshi showed you one article that could guide you through the inputs and analysis of lateral torsional buckling of precast beams. There is much more, a lot of tutorials, articles, webinars, blog posts. So tons of information that you can search through. Then next to this, in the same section of the webpage, you can find the e-learning courses that we call internally the campus. And there you can go through these online courses where you also learn how the software is built, how the software works, how you operate it. There are quizzes inside as well, and once you complete the course, for example, this one for reinforced concrete sections, you can see that takes about 7 hours to complete that, and you can get a certificate proving that you are educated in operation of this application of IDEA StatiCa software package. So IDEA StatiCa e-learning, in the same part of the web page as the support part. Good. And the very last thing from my side is invitation to coming webinars. We will have now the summer break for July and August, and we will continue with our series of educational webinars in September. So that will be a webinar about connection, and in October we are releasing the version 25.1. So we will dedicate a full webinar for the news of that are in this version. All right, and that's the very last word from my side and the last slide. So thank you very much for attending this webinar. I wish you a pleasant day and see you next time.
Thanks for attending. Bye.
Goodbye.